if an atom is so small, how can we know anything about it? By observing its effects. You can't see the wind either, but you can see what it does. And you know from recent history what the atom can do. It's a mighty might, yet it becomes immense when we look inside it and compare the whole to its parts. This, an atom of hydrogen, which is one of the principal elements found in a golf ball, is the simplest of all atoms. It consists of a negatively charged light particle called an electron, which revolves in an orbit about a nucleus. The nucleus of a hydrogen atom is made up of a single particle with a positive electrical charge and is known as a proton. To re-emphasize the submicroscopic nature of our subject, if we could increase the size of the nucleus proton to that of a golf ball, the route of the electron would be about a mile away. Hydrogen is one of the most common elements found in nature. As a gas, it has many uses. One of them is fuel for welders' torches. Scientists have classified and arranged elements according to their atomic structure, and hydrogen, with its single proton, gets first billing. It is assigned the atomic number 1, which refers to the proton. The ability of an element's atoms to form chemical compounds, as hydrogen combined with oxygen to form water, is governed by the atom's electrons. In another form of hydrogen, there's a second particle in the nucleus. It carries no electrical charge, however. In the free natural state, the number of electrons and protons is the same, and the additional uncharged nuclear particle does not affect chemical behavior. We can view it as supercargo, dead weight, a passenger going along just for the ride. It is called a neutron. It gives this form of hydrogen an atomic weight of 2, the sum of the protons and neutrons in the nucleus. Different forms of the same element, with different weights but carrying the same electrical charges and having identical chemical behavior, are known as isotopes. For example, adding this neutron to a standard atom of hydrogen would produce this isotope of hydrogen known as deuterium. This is the hydrogen in heavy water. Adding another neutron produces a third hydrogen isotope called tritium. One rung above hydrogen on the ladder of elements is helium. One of the uses for helium you're probably familiar with is in lighter-than-air craft. A helium atom has 2 electrons and a nucleus composed of 2 protons plus 2 neutrons. So helium has the atomic number 2, same as the protons which it possesses, and an atomic weight of 4, its protons plus neutrons. Going up the ladder, we find elements with atoms that become progressively complicated, with more electrons and increased numbers of protons and neutrons in their nuclei. For example, a neutral carbon atom with an atomic number of 6 has 6 electrons. In the nucleus are 6 protons plus 6 neutrons, so the atomic weight is 12. Carbon exists in many forms, high and humble, as diamonds and pencil points. At the top of nature's ladder is the most complex atom, uranium, with an atomic number of 92. Naturally occurring uranium has 3 isotopic forms with atomic weights of 234, 235, and 238. Uranium and its neighboring elements are maladjusted. Their atoms have an unstable number of protons and neutrons. So observing nature's law against lack of balance and symmetry, they try to become stable by getting rid of their excess nuclear freight. The manifestation of this inner struggle is known as radioactivity. The adjustment may release energy in 3 ways. Beta particles bearing a negative charge are expelled from the nucleus. They are essentially high-speed electrons. Alpha particles may also be shot out. They consist of 2 protons plus 2 neutrons and are positively charged. They are the same as the nucleus of the helium atom. Or the energy may be in the form of gamma rays, electromagnetic radiations like X-rays. Natural radioactivity causes these heavy, unstable elements to decay progressively down the ladder, eventually reaching a stable form of lead. The unit for measuring the rate of such changes or transmutations is the half-life, the time required for 50% of a radioactive material to decay. To illustrate, suppose you had a gallon of whiskey, and each day you drank half the amount in the bottle. The first day you'd drink half a gallon, and the whiskey's half-life would be 1 day. The second day, assuming for the sake of science you'd be able to sit up and take it, you'd knock off 50% of the remainder, or 1 quart. The third day a pint, and so on. But you'd never quite get to the bottom of the bottle. There'd always be a half remaining. The fact that some radioactive matter always remains is not so important as the time required for the half to decay. Half-life varies from isotope to isotope. It takes 4,500,000,000 years for half a hunk of uranium-238 to become thorium-234. The half-life of radium-226 is 1,600 years. That of radon is slightly less than 4 days, while others have half-lives of fractions of a second. So far, we've been watching natural radioactivity. Man has stepped into the act, however, and in some cases outdone nature. Using as his guns cyclotrons and other accelerators, and employing hydrogen and helium nuclei, neutrons, protons, electrons, and other minute bullets, he has made stable matter unstable, produced radioactive isotopes of many elements. He transmutes lithium into helium with a hydrogen nucleus as the projectile. By striking the nucleus of a chromium atom with a helium nucleus, he changes it into radioactive manganese with the emission of a proton. Manganese in turn decays to iron with the emission of a beta particle and gamma ray. And scientists have gone up the ladder above uranium, creating new elements by hitting the nucleus with a neutron. If the neutron sticks, the atomic weight goes to 239, a new artificial uranium isotope. But the nucleus reacts by getting rid of a negatively charged beta particle, thus raising the positive charge of the nucleus by 1 and becoming a new element with the atomic number 93 and called neptunium. Neptunium is a malcontent, and it in turn emits a beta particle turning into element 94, plutonium. Even heavier elements have been developed, but we can stop with plutonium because it's one of the basic ingredients of an atomic explosion.
Reel 2, take 1.
In trying to bring about such an explosion, scientists had 2 recipes, 2 blueprints to follow. The first called for nuclear fusion. To illustrate, here are 4 hydrogen atoms. If fused, brought together under proper conditions, they form 1 helium atom. But a loss of weight occurs during the process. In other words, the parts are heavier than the whole. Why? Because when the fusion takes place, this extra mass or weight is converted to and released as energy. Energy which might be put to some use. The sun has the key to this combination. It is continually converting hydrogen into helium and sending the resulting energy earthward. That's the principle which might make a hydrogen bomb work. But to the scientists who wanted a quick solution, releasing a piece of the sun on Earth for a moment of devastation seemed a bit impractical. So they went to the upper end of the ladder and set about getting atomic power through the reverse of fusion by breaking heavy elements into lighter ones by a process called fission. Like this. When hit by a neutron traveling at a certain speed, the nucleus of a uranium-235 atom breaks up into 2 much lighter elements, with a tremendous release of energy from that which held the tightly packed nucleus together, like this. While it seems inconsistent that both building up and breaking down of atoms releases energy, This is only possible at the far ends of our ladder of elements, where fusion produces energy through the combination of the lightest elements and fission splits only the heaviest. The products of fission and fusion tend toward the middle of the ladder. In the case of fission, the possibilities seemed immense and workable. The scientists knew that the fission of 1 pound of uranium would produce as much energy as the combustion of 1,400 tons of coal, or 250,000 gallons of gasoline. The question was how to do it, how to produce the breaking up of the millions of atoms in a comparatively massive hunk of uranium and do it instantaneously, so that instead of a gradual release of smooth power, as demonstrated by a moving locomotive, the energy would be built up, then let loose in a violent explosion. A path was indicated by the fact that fission of a uranium-235 nucleus by one neutron creates, in addition to the fission products and energy, 2 or 3 new neutrons. Perhaps these neutrons could be put to work in developing a chain reaction. This is an example of a chain reaction sustaining itself. This is one that builds up to a big finish. If several neutrons could be produced in a single fission of a uranium atom, and these neutrons in turn could be used for further fissions, then a chain reaction would be developed, which would reach a colossal climax. The energy liberated by each fission step would be let loose in a mighty explosion. They knew that uranium-235 was good fissionable material. They also knew it was scarce. 1 part in 140 of natural uranium is 235. An insignificant amount is 234, and the rest is 238, which wasn't a suitable ingredient. It was hard to extract the good from the bad because, being isotopes, both had the same atomic number of 92, therefore the same chemical behavior. The very slight difference in atomic weights, however, made possible several ways of achieving the separation by physical means. If natural uranium gas is passed along one side of a porous barrier with a greater vacuum on the other, the lighter 235 atoms will go through the barrier a bit faster than the 238. By this process, it is possible to enrich the uranium with the 235 isotope, enrich it enough for fission purposes. The Manhattan Engineer District team of scientists, engineers, industrialists, labor, and military built huge plants to produce the stuff by this and other means. The scientists went further, taking advantage of the fact that uranium-238, instead of fissioning, tends to capture neutrons to ultimately become plutonium, and plutonium is as effective for fissioning as uranium-235. The Manhattan Engineer District team built a plutonium plant at Hanford, Washington. Our bomb builders were nearing the goal. They had the substance. Now for the shape. This isn't it, and the reasons become obvious when we hit the block with a neutron and follow the careers of the 3 neutrons we assume are formed by the initial atom split. This neutron enters a nucleus without causing fission. It's captured. It's a dud. These 2 escape. This is then a hunk of fissionable material in which the neutrons accomplish nothing, and in which a chain reaction can't even get started. It's called a subcritical mass. The problem of the scientists became clear: to make fullest use of all neutrons produced in a single fission. A big step toward their goal was to prevent the escape of the neutrons. Here, 1 of 3 neutrons makes good, fissioning another atom and starting a chain. Our material is now called a critical mass. This would be fine for an atomic power plant, but it isn't enough for an explosion. To get that, we must keep the birth rate of the neutrons well above the death rate. 1 neutron must produce 2, 2 must produce 4, and so on. Then we'll be in business. One way to cut down neutron loss and increase the number of fissions is to give them more working room. Yet, Since we are dealing with bomb material, we must economize on size. So the best shape is a sphere, which has minimum surface area through which neutrons can escape, with maximum volume in which they can work. And we can further decrease neutron loss by covering our bomb with a special mirror, which will reflect the neutrons, turn them back into the field of play. When we get a successful chain reaction growing, we have what is called a supercritical mass. And our situation is also supercritical, because we aren't ready for an explosion. We must keep our supercritical mass divided into subcritical parts until the proper time. When the explosion is desired, the parts are brought together quickly and kept together long enough for a great number of fissions to occur. The time for our bomb to explode is less than a millionth of a second. In building our bomb, we've been playing a game, toying in a broad general way with theories already worked out in detail and executed by those who during World War II developed and produced the most destructive weapons of all time. Theirs was a dramatic role and a precarious position. They couldn't experiment realistically along the way. They couldn't conduct small, safe, pint-sized tests. There's no such thing as a small, safe atomic explosion. Below critical size, the bomb is a bust. Above, it's a burst. Compromise wasn't possible. To those who early on the morning of July 16th, 1945, awaited the setting off of their first atomic bomb, it had to be all or nothing. But which? The answer left no doubts. Teeing off on the subject of the atomic bomb requires that you focus your attention properly. Keep your eyes where they belong, on the ball, because it serves to lead us into a minute universe containing things so infinitesimal they are hard to imagine, unless we change our concepts of size and space. And the change comes easier by taking a quick glimpse of golf, a game involving the manipulation of a small sphere, the ball, on the surface of another sphere about 300 million times as large, the Earth. For a golf ball is about 300 million times as large as each of the atoms which make up its elements. And hydrogen, with its single proton, gets first billing. It is assigned the atomic number 1, which refers to the proton. The ability of an element's atoms to form chemical compounds, as hydrogen combined with oxygen to form water, is governed by the atom's electrons. In another form of hydrogen, there's a second particle in the nucleus. Increase the size of the nucleus proton to that of a golf ball, the route of the electron would be about a mile away. Hydrogen is one of the most common elements found in nature. As a gas, it has many uses. One of them is fuel for welders' torches. Scientists have classified and arranged elements according to their atomic structure. It carries no electrical charge, however. In the free natural state, the number of electrons and protons is the same, and the additional uncharged nuclear particle does not affect chemical behavior. We can view it as supercargo, dead weight, a passenger going along just for the ride. It is called a neutron. It gives this form of hydrogen an atomic. If an atom is so small, how can we know anything about it? By observing its effects. You can't see the wind either, but you can see what it does. And you know from recent history what the atom can do. It's a mighty might. Yet it becomes immense when we look inside it and compare the whole to its parts. This, an atom of hydrogen, which is one of the principal elements found in a golf ball, is the simplest of all atoms. It consists of a negatively charged light particle called an electron, which revolves in an orbit about a nucleus. The nucleus of a hydrogen atom is made up of a single particle with a positive electrical charge and is known as a proton. To re-emphasize the submicroscopic nature of our subject, if we could increase